Okay, so I am really excited to be talking to you today about genuinely one of my favorite subjects, which is dimensionality reduction. You'll probably kind of get the sense as this talk goes on that I'm a bit obsessed with dimensionality reduction, maybe a bit too obsessed with it. I don't expect you to leave this talk as obsessed with this subject as I am, but hopefully you'll come away with, maybe a new appreciation of dimensionality reduction. Maybe this is your first introduction to dimensionality reduction, and above all, some really practical ways that you can use this to get more meaning out of your data. Okay, so just to start us off, I'll do the kind of poll that I feel like is kind of obligatory in these kind of talks, just to find out how much you guys know already. So I've put some keywords at the top here because often we use different words when we talk about dimensionality reduction. So you might think, oh, I don't know about this topic, but actually I know about PCA, or I know about feature selection or feature extraction already. So taking all of that into account, just by way of show of hands, who would say they know little or nothing about dimensionality reduction? Okay. And same question again, how many people say they know something about dimensionality reduction or they've played around with it before? Okay, so most of you. And who would say, I already have a pretty solid understanding of dimensionality reduction or regularly work with it? Yeah, okay, a few of you. Okay, so quite a mix. So that's always the challenge with these kind of talks. How do you aim the talk at all the different levels in the room? I've done my best to kind of, take everyone along with me, so no prior knowledge assumed. But even if you know a lot already, hopefully there's going to be a bunch of new stuff here. And the other thing as well is, in my organization, like everyone knows about dimensionality reduction, even the cleaner, the secretary, it doesn't matter, mainly because I go on about it all the time. But I actually think that it's really valuable, right, if you can explain this stuff, which can sometimes be quite complex, in a simple way to, maybe your non-technical colleagues or your customers. So I think that's going to be one of the aims of the talk as well. Okay, so a bit of a schedule of what we're going to talk about today. So we're going to kick off with just an overview of dimensionality reduction from a high level. Like, what is it? Why would you even want to use it? Then we're going to look into the specifics of 4 dimensionality reduction techniques. So today we're going to look at PCA, random projection, isomap, and TSNE. So if that sounds intimidating, then don't worry, we'll go into detail on each of those. But those are what we're going to cover today. And then the last part of the talk, which is kind of my favorite, we'll look at some of the cool things that you can do with dimensionality reduction, some of the kind of amazing applications of it. And then we'll try and leave some time at the end for questions. And a couple of notes about my approach with this, because again, we can approach dimensionality reduction. It's a huge subject. We can approach it from a load of different angles. I've basically chosen to emphasize a bit more on intuition, keeping things clear, rather than something that's like very mathematically rigorous. There's a lot of mathematics once you go into the nuts and bolts of dimensionality reduction. To be honest, it's probably too much for a talk of this length, unless you have a lot of math background already. So for the most part, we skip the maths. Dimensionality reduction can be used for a lot of different things. So it can be used as like a pre-processing step often for machine learning. It can speed up a lot of machine learning algorithms. It can be used for things like word embeddings and natural language processing, which we'll touch on later. But mainly I've focused on visualization, right? How you can see your data in new ways. Originally, I put a load of code in the slides, but then I got some feedback of a draft of this talk. And basically, the feedback was, the code wasn't super helpful, so super useful, because people come from different languages. Also, a lot of this stuff is very easily Googleable. If you want to know how to do PCA in Python, just Google PCA in Python. Probably not the best use of your time to listen to me, going through code examples. So instead, I've focused much more on, okay, do we really understand this? Do we know when to use this technique versus this technique? But I will be putting some code up on GitHub after the talk. Okay, so let's start off just by thinking about what dimensionality reduction is and why do we care? Why should we use this? And I think this is probably best illustrated by a true story of something that happened to me recently. So I was talking to a friend, and my friend runs a startup, right? And the startup is a sort of B2B software startup that services big brands and basically charges them a subscription, right? And my friend's startup was kind of in some difficulty because they had problems with customers canceling, they weren't really sure who to target for sales, and he was finding this really difficult. And my friend, though, he's not a technical person, but he is, like me, a data geek. So what he'd done is he basically compiled a huge amount of data on all of his customers in something that basically looked like this. This isn't the actual spreadsheet, but it looked something like this, right? I'm sure we've all seen spreadsheets that look like this, just kind of data vomit, every possible thing all clumped together. And this was basically data on his customers, right? So it was things from, how long had they been a customer, how often were they visiting the site, how many support tickets were they opening, what pages were they visiting, what was their bounce rate, all of this kind of really rich data. So he had a really large amount of useful data here, but he just couldn't understand it, which is, relatable, right? How could you possibly understand this? You try a couple of things, pick a couple of columns and maybe build a chart or something like that, but he just couldn't understand this. So I suggested, well, have you tried dimensionality reduction? And he said no. And so we took this data and we just did some really simple dimensionality reduction on it using PCA. And again, we'll talk exactly about what that means in a second if you don't already know. But just to touch on what that means, we're basically taking every row in this spreadsheet, each of which represents a customer, and we're then transforming them into a point in 2D space. And if we do a good job of dimensionality reduction, the customers that are similar, based on the data in this spreadsheet, should be close together. The customers that are very different should be far apart, right? And we ended up with something like this. So I've jazzed this up a bit. I've changed the brands, but effectively, this is the kind of thing that we ended up with, right? And this was immediately super powerful to him because he not only understood the data in a new way, but he had something that was actionable. Because these guys who I've highlighted in red, these are customers who had cancelled their subscriptions. They had churned, basically. So he was able to realize, oh, shit, based on the usage patterns, Disney, or the brand represented by Disney here, they're probably pretty close to cancelling. I didn't notice it, but based on their usage patterns, they're a very, very similar kind of customer. So I need to get on the phone to them, go into their offices, make sure they're understanding the software, they're getting value out of it. On the flip side, the brands highlighted in green, these guys had upgraded to the sort of top-tier subscription. They were the customers who loved the software. And again, he wasn't aware, but the brand represented here by Samsung, they also seemed to just love this software. But he hadn't realized that. And so, again, he had an action point. Get on the phone to them, say, hey, would you be interested in a premium subscription? So this is just one illustration, and we'll see a bunch more, but of where dimensionality reduction helps us not just make our data more understandable, but more meaningful, which for me is like the whole point of visualizations, right? You can have a visualization that's like clear, that looks really nice and looks really beautiful, but if you can't immediately see the meaning, it's not doing a really good job. Here's another example that I really like. This comes from Victor Powell. So this is some real data, and it's basically looking at diet in all of the UK's principalities, so England, Scotland, Northern Ireland, and Wales. So I just want you to look at this visualization and just try and absorb the meaning from it, if you can get any meaning from it. What can you say about the diets in these different countries on a high level? Is there any that particularly stand out? Are there any that look particularly similar? Now, to me, this visualization is very clear, right? There's nothing strange going on. It's laid out quite nicely. It's fine, right? As a visualization, it's attractive. It's fine. It's clear. But for me, it's quite difficult to get meaning out of this when you're looking at so many different dimensions. So let's see what, again, happens if we employ PCA, dimensionality reduction. We get this. Now, this to me is like really interesting. I don't know about you guys, but I had no idea that this was kind of the relative diets in these different countries, and basically, especially how different Northern Ireland is. Just out of interest, do we have anyone from Northern Ireland in the room at the moment? Okay, one person. So apparently you're the odd one out. Statistically speaking, your diet will be very different from people from England, Scotland, Ireland, and Wales. And also another thing that surprised me is that Scotland and Wales, are also more different, and England is kind of a middle ground in between them. Again, I definitely didn't pick that up looking at the data just in its original form. So you can get a lot more meaning from dimensionality reduction. When you're looking at this versus this, you just get a lot more meaning. And so that's the key point. Yes, do you have a question?
What was influencing the overlaying being?
Yeah, it's a good question. So the question is, what's the difference? What makes the Northern Ireland so different? I mean, if you look at it, there's a bunch of different things, and there are a lot of subtle differences, or maybe not so subtle differences, but they kind of compound. So you can see, like, alcoholic drinks is much lower. Potatoes is much higher, I guess, matching the stereotype. There are a bunch of different things where fresh fruit is a little lower. There are a bunch of subtle differences, right? No one necessarily jumps out at you and makes you think, oh wow, these guys are really different, which is kind of the point, right? Nothing jumps out when you're looking at all the data at the same time, but when you add all these little differences together, you get something that is quite starkly different when you're looking at in 2 dimensions. So yeah, this is the quest, getting from something that's understandable to something that's more meaningful. So let's dive in now to exactly what's happening when we did this process, right? When we went from this big spreadsheet with lots of dimensions to something that looks like this. Like, what exactly is going on here? How do you do this in practice? What's going on here? Okay, so there's basically 2 different ways that we can perform dimensionality reduction, where we can go from a large number of columns to a small number of columns that's going to allow us to plot the data in 2D. So we can either do feature selection or feature extraction. Now, spoiler alert, we're almost exclusively going to do feature extraction, right? So feature selection is not going to be used very often in practice, but it's a little simpler to understand. So we'll start there and then kind of move on to feature extraction and what that's all about. So to illustrate this, let's imagine that we work for a car magazine, right? So I personally don't really read car magazines, but from the little I do understand about them, they'll often contain a lot of stats about cars, right? So maybe you want to buy cars, or maybe you're just interested. You want to stack up the various different dimensions that make up a car. So it could be things like, what's the horsepower? How quickly does it go from 0 to 60? What's the max speed? And then you have cost factors as well, like the price, but also what's the miles per gallon? What's the road tax on it? So, and I just also just underline that point that we kind of can already see some clustering maybe, where you have some features that are related more to the performance of the car, some features that are more related to the cost of the car. So if I have something like this, it's great, the tabular form is fine, but maybe I want to be able to take all of these different cars and lay them out in a visual way so I can see, okay, which cars are similar and which cars are quite different. Well, the problem is that if I do this, I'm going to need a y-axis and an x-axis. So one thing with dimensionality reduction, for visualization at least, we're always pretty much going to be aiming for 2 dimensions, right? Which sort of makes sense. Yeah, because we can only really represent 2 dimensions for visualizations. If we go really fancy, maybe we would go for a 3D visualization, but that's not very normal. So we need 2 dimensions here. So feature selection is basically the most naive approach, which is to just say, hey, okay, let's just get rid of 4 of our dimensions, 4 of our columns here, and let's end up with 2. So let's say at random we pick horsepower and price. Well, then we can very easily make a 2D plot of horsepower plotted against price, right? But how do we actually select features in a more intelligent way? Okay, so to answer this question, I'm going to ask you all to do an exercise. So I want you to imagine that you're drawing a horse, okay? So I want you to imagine drawing a horse in your mind, try and picture that as clearly as possible, okay? Everyone got a drawing of a horse in their mind, okay? Right, I'm going to show you 3 drawings of a horse now, okay? These are done by me, so apologies for my artistic skills. What I want to know is, by a way of show of hands, okay, when you're thinking of that drawing in your mind, how many people's horse look like A? Okay, how many people's horse look like B? Okay, 2 people. How many people's horse look like C? Okay, 1 person. Okay, interesting. Okay, so clearly there's a trend here, right? We all went for the horse that looked like A. And that's kind of interesting, right? Because when you think about it, there's no rule book that says we have to draw a horse like this. And actually what's happened here is is feature selection, right? So, and by the way, some of you could have decided to have a really artistic angle and, a 3D horse or whatever, but probably most of you, imagine like a flat plane or something close to it. So why have we all gone and chosen A? We've basically decided to get rid of the width of the horse as opposed to getting rid of the height of the horse or the length of the horse. It's actually a really good question. Now, one theory that we might propose is, okay, we want to preserve the longest dimensions, because this is what's happening. In this case, width is the shortest dimension, so maybe we get rid of that. Although that theory already starts to break down a little bit when you think, okay, what was your second choice? Because probably for most people, your second choice would have been B, right? Whereas that, again, isn't preserving the longest dimension in this case because a horse is longer than it is wide. So it's maybe not about length. And we can illustrate this even more if we look at a picture of this house. So notice that this house is longer, or is deeper than it is wide. But we would probably all, again, choose to draw drawing A, the front of the house, even though those aren't preserving the longest dimensions. And basically, the way that we can explain this is we, human beings, even as children, we're trained to keep the dimension that contains the most information. So there's a lot of information in drawing A in these dimensions that we've kept here, not so much in B and not so much in C. Another way to think of it is a lot of variance, right? So information and variance, they're kind of two sides of the same coin. Again, there's a lot of stuff changing in image A. You've got your windows, your doors. In B, it's pretty uniform, right? So it's not as interesting to capture. It's not as important to capture that. One thing I would note is that when we talk about preserving information or preserving variance, this could also be a bit contextual, right? So look at these different pictures of a chessboard on a table. What you preserve might depend on the context. So I would probably take picture C over the others if I wanted to know about the chess game, about what the current status of the chess game was. But if I wanted to know more information about the table, like the dimensions of it, then A or B would be much better. So information can be contextual. That's something that we'll see a lot later as well. Okay, so how would we do this in a sort of data science way? Well, a sort of simple approach is we could first of all scale these features so that they're the same size. We could calculate the variance for each of them, and then we could just keep the two columns with the highest variance that kind of capture the most information. And in this case, I think that would be horsepower and road tax. Okay, so I'm not going to dwell on that too much because, as I said, we won't tend to do that very often, but that's theoretically how we would do feature selection. The only time we really use feature selection a lot in practice is for removing redundancy. So if I have redundant features, so you can see like if I have my max speed in miles per hour and kilometers per hour, I'm not really gaining any information by having both. So in this case, these features are redundant. I can just get rid of them and I haven't really lost any info. Okay, so that's feature selection. Now here's the interesting part, which is feature extraction. So feature extraction goes a step further and says, right, rather than just getting rid of some of my features, get rid of everything apart from horsepower and road tax, let's say. How do I build new features? So for example, build new features for performance and cost that capture multiple dimensions in one. There are three ways to think about what we're doing when we're doing feature extraction. We can think of it that we're creating new dimensions. I personally find that's a bit of a confusing way to think about things. You can think about it as combining existing dimensions. Okay, so I think this is a little bit more on the money. Okay, we're maybe taking existing dimensions and merging them somehow. Or another interesting way to think about it, and we'll see this in a second, is that we're compensating for the dimensions that we've lost. So rather than just throwing away a dimension and sort of saying, that's life, we're taking the information that was in there and trying to apply that to the dimensions we still have. Okay, so here's a little illustration of this. So let's say that I'm doing some experiment. I'm talking on walkie-talkies with my friends, and I want to produce a diagram of our relative positions. So I'm at the top of the shard in green. My friend Bob is in red, he's on Tower Bridge, and my friend Charlie is in blue, he's at the base of the gherkin. Okay, so that's where we are relative to each other. And we can see this in 3 dimensions, so we can see that not only are our latitudes and longitudes different, but my altitude is different, right? I'm much higher up than the other 2 guys. So I decide that I want to represent this in 2D rather than in 3D. Okay. Now, the first decision that I need to make is, what do I want to preserve? Because I can't preserve everything, unless I have redundant information. When I lose dimensions, I'm going to lose some info. Yeah, it's inevitable. But what do I care about preserving? So, for example, I might decide that I care about preserving the angles between us, between myself, Bob, and Charlie. And this is exactly what we see when we look at a world map. So you guys might know about this already, but this is the world map that we're all used to seeing. But this is a specific projection of a globe onto a flat plane, a flat rectangle. It turns out that you can't do that without losing a bunch of information. And so this projection, which is called the Mercator projection, is basically preserving angles. Yeah, so it means that the distances are all messed up, the sizes of countries are all messed up, but the angles are the same. And that's because in the 16th century, when this was conceived of, navigation was the main reason you used maps. So you needed to know the exact angle that you needed to go to get from point A to point B in a ship. But a lot of people say this is now not really relevant. Some people say it even kind of enforces some prejudices and racism because, for example, it skews the sizes of countries. So Western Europe looks big, whereas Africa looks disproportionately small. So you have projections like this is, I think, called the Gall-Peters projection, which keeps the sizes much more accurate at the expense of angles, for example. So you can see Africa's much bigger. Again, this could be a whole 90-minute talk on its own, but kind of an interesting note that even when we're thinking about things like maps, we have to decide what information we want to preserve, right? So for the purposes of my experiment, I decide that I want to preserve distance. And when I talk about distance here, I basically mean Euclidean distance. So basically the regular distance from point A to point B as the crow flies. Okay, so what if I do feature selection here? And I just say, okay, let's just ignore the third dimension. Let's ignore the height dimension. And let's just collapse these points just down onto the ground. Well, the problem here is, as you probably noticed, it's accurate in terms of the latitude and longitude, but the distances aren't preserved because remember, I'm up really high and this isn't really reflected in this feature selection. So what can I do? Well, quite simply, I can just move myself a little further away from these other two guys. So now it's not accurate in terms of angles and the exact locations, but in terms of distance, I've preserved the distance. So I've just taken that height distance and then said, okay, well, I'll just move myself further away from these other two. Here's another way to think about it. When I'm doing feature selection, I'm just projecting just directly onto the flat plane. Yeah? So just these things are just going to fall straight down onto the ground effectively. But I don't have to do that. I can actually decide to tilt my plane a little bit. So just before I do this, notice that where I am, I'm basically to the right of this bold line on the left here. If I tilt the plane, the distance between Bob and Charlie is going to remain the same, but now notice that I'm effectively more distant as I tilt the plane. So rather than just projecting down onto the flat surface, I've tilted the plane, and that's meant that when I then readjust this and visualize this in 2D, I'm going to be further away from these two guys. Yeah. So this is just another way of thinking about it. One you might find more confusing, one you might find more intuitive. Again, it's just the difference between, do you think about it as combining existing dimensions or compensating for dimensions you've lost? Again, this is the same thing, this is the same process. But the key thing is we're taking information from both dimensions, right? So if we think about how this could work when applied to our magazine example, basically what we could do is we could say, okay, let's scale our price dimension. Let's just scale that from 1 to 10 to come up with something like this. And then what I'm going to do is I'm going to just remove my other dimensions, miles per gallon and road tax. But where these are particularly high or particularly low, I'll just use that to compensate and adjust my cost dimension. So I get rid of my miles per gallon, but then increase or decrease the cost as appropriate. And do the same for road tax, increase or decrease as appropriate. And then I'm kind of going to end up with a dimension, this cost dimension, that's going to keep all of the information in all of these dimensions. And this is how I could end up with something that maybe looks like this. Okay, big caveat to this though. The one thing dimensionality reduction doesn't typically do for us is interpret our dimensions. So we probably wouldn't be in a position where we can just say, yeah, that means performance, that means cost. We're going to end up with these slightly mysterious dimensions, which are going to be a composite of our other dimensions in our data. And interpreting that can honestly be quite tricky. We'll touch on a little bit later on about how we can maybe unpick and interpret those dimensions. But yeah, we're not going to get anything as quite as semantic and understandable as that. Okay, cool. So let's get into the details of 4 dimensionality reduction techniques specifically. So the 4 techniques that we're going to look at are random projection, principal component analysis, isomap, and TSNE. So you might have heard of some or all of these already. Basically, there is a sense in the ordering where we're going from the simplest to the most complex. We're going from, computationally speaking, the fastest to the slowest. Now, even though principal component analysis isn't the fastest or the simplest, it's going to be easiest to start here, because this is our oldest dimensionality reduction technique. It's over 100 years old. It kind of forms the basis for a lot of the work that built on it. Okay, so to understand principal component analysis, commonly known as PCA, we're going to get some help from our good friend, Donald Trump. If you've been following the election, you know there's a lot of controversy over the election because Donald Trump lost the popular vote. And so this is a subject that he's quite sensitive about. He lost the popular vote, but in the States, it depends on how many electoral college votes you get. So he won the electoral college. So there's a lot of dispute about how big Donald Trump's election victory is. So here's a graphic which shows all of the past 10 US presidents, and at the bottom here you see how big their electoral college win was, which is what gets you into the White House, and then on the y-axis you see what was their percentage of popular vote. So when we're doing dimensionality reduction, normally we'll be going from a high number of dimensions, 10, 100, a million dimensions, to 2 dimensions. But it's actually easiest to demonstrate this going from 2 dimensions to 1 dimension. So going from 2 to 1 is effectively ranking. Yeah? How do we rank these presidents from best to worst? So one thing we could do is feature selection, right? So we could just say, okay, I'm just going to ignore 1 dimension. Let's say that we're going to ignore the electoral college vote and just focus on the popular vote. So that means basically we're going to project all of these presidents onto that straight line, onto the y-axis, and just see, okay, how did they do in terms of the popular vote? And you can see that if we do that, then Donald Trump is going to be third from bottom. So one of the worst presidents in terms of popular vote. He's probably not going to be very happy about that. Maybe we need to take a look at why he's not happy about that. Well, does he have a legitimate complaint? Well, possibly, right? Because what you can say here is these lines, which kind of represent our residuals, we might say, which is kind of the distance that these presidents have to travel, is pretty high. And we also want to think about information loss. So with PCA, like with my example, we want to preserve distance. Specifically, we want to preserve pairwise Euclidean distance. So that means that if things are far apart in the 2-dimensional space, in the 1-dimensional space, they should be far apart as well. Well, that doesn't really work very well, because if you look, for example, at Jimmy Carter and Ronald Reagan, they're at opposite ends of the scale in 2D, but then when we go into 1D on this projection, they're going to end up at the same point. So we're losing a ton of information there. So, okay, maybe Trump has a legitimate complaint. Well, what about a different projection? What about if we instead look at electoral college vote and we ignore popular vote? So we'll get something like this. Trump is probably going to be a lot happier here. He's going to be the 6th best president ahead of JFK, so he's probably going to be quite happy about that. What can we say about this projection? Well, it's arguably a little bit better than the last one. If you look at the residuals, they are smaller overall. There's some distortion, so LBJ ends up pretty much neck and neck with Ronald Reagan, which we don't see in the 2D space, but this is much, much better. And so this already gives us a clue that the optimal projection is going to be closer to this than the previous projection that we saw. So what PCA is going to do is it's basically going to find that optimal projection line, the line that minimizes these residuals, the amount of distance they have to travel when they're going to this optimal line. And so in this case, you can see that Trump is probably, he probably can neither complain nor brag about this, which probably kind of is what we want, right? We don't really want to be improving anyone's position. We don't really want to be kind of subtracting from anyone's position if we can help it. We want to preserve as much info as possible. Again, unless these were already on a straight line, we couldn't preserve the full amount of information. It's just not really possible, but we can preserve as much as possible. So what we're going to do then, once we've figured out what this optimal line is we're going to track their positions along the line, each president's position along the line. So maybe George W. Bush starts at 0, then we go to Nixon, Carter, and we'll trace their position along this line. But what we'll also do is we'll trace their position sort of up and down off of this line, right? So we'll see how far they had to move when we projected them. And this is going to be stored in what we call our principal component 1 and our principal component 2. So what's kind of cool about this is, in the first instance, we capture all of the information. We capture enough information to reconstruct our data perfectly, or at least their relative positions perfectly. So, and we'll see this whenever we do PCA, even if we do it on 100 dimensions, we'll, in the first instance, usually come up with 100 principal components. And we'll see this is quite useful later on. And this, by the way, is what we see once we project them onto the line. So you can see, again, there's a bit of movement, but relatively speaking, generally speaking, all the presidents kind of maintain their relative standing. Okay, so what's actually happening when we do PCA? Well, this is kind of a visualization of what's going on, one visualization of what's going on. So you can see the residuals are growing and shrinking as we move this line. And basically, we're trying to get to the point that minimizes the residuals, right? And that's shown by these pink ticks here. So that's one way of thinking about it. Another kind of visualization which I kind of like is you can think of these red lines as like springs with equal tension. And so basically we're waiting till we reach a point of equilibrium with all of the springs. Now, the only thing that's slightly misleading about these graphs is it might make you think, with PCA we normally take an iterative approach. We do something like gradient descent where we slowly kind of close in on the answer. Now it turns out we can actually do that, but most of the time we won't do that. We'll actually use a method called SVD. So a lot of people get mixed up between like PCA, SVD, eigendecomposition, because they kind of overlap a little bit. But principal component analysis is basically the outcome that we want, where we have these principal components which measure the greatest variance in the information, where we're preserving the greatest amount of information possible. Singular value decomposition is basically just a mathematical technique that we commonly use to do this. And singular value decomposition is a kind of generalization of or extension of eigendecomposition. So again, I won't go too deeply into the maths, but it's all about finding eigenvectors and eigenvalues of the covariance matrix of this data. This is what's normally done. We can do gradient descent. There are situations where we might want to use gradient descent with PCA. So for example, if we didn't have all of the data up front, we were doing online learning, or if we wanted something a bit more robust to outliers. But this is the normal approach we'll take, SVD. Now, again, I won't get into SVD and what it is specifically. You can just know it's a mathematical matrix technique, series of matrix operation. But here's the sketch of what it does. So you can imagine drawing a sort of ellipse around this data. Yeah? And let's say it's a 95% confidence ellipse, which means it will contain 95% of the data points. So once we've got that ellipse, we can basically say, okay, what's the length and what's the width of this ellipse, and in what direction do these axes face? Okay, so the longest axis is going to be our principal component 1, and the shorter axis will be our principal component 2. And if we were doing this in higher dimensional space, obviously this would generalize to higher dimensions. Now, one thing you might notice here is, okay, well, what if our data is basically like a circle? Well, it's a good question, and of course, if we do this, then principal component 1 and principal component 2 will basically be the same length. So it doesn't really matter which one we pick in that case. We're also going to lose a ton of information in that case, sort of inevitably. So this PCA only really works when our data is somehow squashed, like this. But the good news is in higher dimensional space, it always will be, and we'll usually end up with pretty good results. One thing that you might be wondering is, or you might think, is PCA seems a little bit similar to linear regression, which is a good observation. So it definitely does have some overlap here. I don't know what people's experience with linear regression is, but basically the big difference is here we're looking at the residuals in terms of the direct distance to the projection line, whereas if we were doing linear regression, our residuals would look like this, right? So we would say, okay, what's the error if we were trying to predict, say, popular vote based on someone's electoral college vote? Yeah. Now, one thing that is true is that if we do a linear regression trying to predict popular vote based on electoral college vote, and then do the other direction, we try and predict electoral college vote based on popular vote, the line that we'll get from PCA will always fall in between them. Okay, and this is something that the author of PCA in the original 1905 paper, which I recommend you go and read if you're interested, also observed. So that line of best fit will always lie between the two regression lines. So that's kind of interesting. And as I mentioned, we'll usually end up with the same number of principal components as the number of dimensions in our original data. What's kind of cool about this, and this doesn't apply so much for visualization, but is useful for other techniques, is we can figure out how many dimensions we want to keep. So there's this concept of a scree plot you might have come across, where we plot the number of dimensions and we can say, okay, how much information, how much variance am I losing when I go to, I don't know, 8 dimensions versus 4 dimensions versus 2 dimensions. And so you can use that if you want to choose a number of dimensions based on an acceptable information loss. Okay, so the summary for PCA is we're going to preserve pairwise distances, the distances between 2 points as much as possible. The pros are, it's pretty fast. We get to choose how many dimensions we want to keep. And it's fairly easy to understand the algorithm. The cons, so we haven't talked about this, but we're going to see later on, this doesn't work so well if the data is nonlinear. So let's say image data. It can be still quite expensive with very large data sets where you have billions of dimensions. And it's sometimes not super robust to outliers, although, as I said, we can use things like gradient descent to try and help this. Okay, cool. So let's go on to our second technique, which is random projection. So random projection is kind of very simple and very mind-bending at the same time. Yeah, really understanding it will take a long time, so we're just going to skim over it. Okay, random projection, basically, if you look at PCA, what we just did with PCA, the line that we chose was data dependent. So we looked at all the data and we decided, okay, what's the best line? Which makes a lot of sense, right? Like, why wouldn't you look at the data when you're choosing your line? So a question that you could ask is, well, what happens if I just choose a random line? If I just put on a blindfold and I just go like this, yeah, and randomly draw a projection line that looks like this, or looks like this, or looks like this? Well, the answer in this case is it doesn't go very well, right? This, for example, is a very bad projection line where I'm going to lose a ton of information. But what is counterintuitive and counterintuitively true, and which was proven in the kind of mid-80s, is something called the Johnson-Leidenstrauss lemma. So yeah, don't worry if this equation is not immediately clear. We could probably stare at this for an hour and it wouldn't make sense. Maybe for some of you it is clear, but here's a sort of more plain English summary of what it says. Basically, it says that if we have points in a high-dimensional space, we can embed them into a much lower but still high-dimensional space in such a way that the distances between the points will be nearly preserved. What this means in practice is that we can basically just pick a random line, plane, or hyperplane. I mean, in this case, it will always be a hyperplane because we're going to a high dimension still. Our target dimension still needs to be quite high. And it's going to perform okay as long as the source and target dimension are high, even if we pick it at random. Yeah, so again, it's kind of like a bit mind-blowing or mind-bending to me that we can just do this randomly, not even look at the data, and we'll still get a reasonable result. The only thing that we'll do is we'll pick our numbers randomly using a normal distribution, so numbers in the middle will come up a little bit more often than numbers at the end. And you can see this empirically. This works when we're dealing with high dimensions. So here we're going from 600 to 0 dimensions. The blue line is PCA, which performs very well, gives us very little distortion or error as we move down the dimensions. You can see random projections, which are represented in green. It kind of keeps up with PCA until about 350, 300 dimensions. It performs basically the same, right? Once we get into low dimensions, it goes a bit crazy, and by the end, it's just a disaster, right? So you definitely don't want to use random projections for your entire visualization. It's not going to work. But let's say we were going from 1 billion dimensions to 2 dimensions. Well, if we do PCA on that, that's going to take a really, really long time. So what we could do is use random projections to go from 1 billion dimensions to, let's say, 1,000 dimensions, and then use PCA to then get to our 2D image, our 2D visualization, and it's probably going to look pretty much the same. So it's kind of counterintuitive, but it's true. Again, the maths proves it, and it's a really useful technique if we're dealing with these really high dimensions. So the summary for this one is it preserves pairwise distances, sort of. It is very, very, very fast. It doesn't need to look at the data at all, and it can be used nicely in combination with PCA. The cons, of course, is that you can only do so much with it. You really need to use something like PCA to take you to the point of being able to do visualizations, because things get weird once we reach low dimensions. And it's pretty much the same as PCA in that it assumes linearity in the data. Again, that's something we'll talk about in a second. Okay, so now let's talk about ISOMAP. So this is a really interesting one. Just by way of show of hands, who's come across ISOMAP before? Okay, so if you've ever read or done anything to do with ISOMAP, very quickly you'll start hearing about Swiss rolls. So this is very strange, but there's this thing that's apparently very well known called the Swiss roll problem. You might know about it already. When I first heard about it, I thought it was something to do with bake-off, but no, apparently this is a real data science kind of conundrum. It's often talked about in the context of ISOMAP. So if you do a Google image sort for ISOMAP, you'll see a lot of images like this, a lot of images of these sort of Swiss rolls. So basically the whole thing of the Swiss roll problem is if you look at data that's shaped like this in a kind of Swiss roll form, then techniques like PCA will basically cut the Swiss roll, which means that the blue stuff is going to be close to the red stuff, whereas ISOMAP is going to basically use a manifold represented by the pink line, and it's going to unfold the Swiss roll. And apparently this is really good. We always want to unfold our Swiss rolls. To be honest, I found this super confusing when I first came across it, even though this is constantly the way that ISOMAP is explained. We'll come back to this, but I don't think this is a particularly good way of explaining this. I'm going to use the president's example again to try and understand ISOMAP. This, as a kind of disclaimer, this starts to get a little bit more difficult to understand, but I think we can still do it. So, sorry, I want to flag up on this president's visualization a couple of interesting things. So Trump is very close to Nixon. Okay, these guys are very close neighbors. Equally, JFK and Jimmy Carter are very close to each other. They're very close neighbors. They had very, very similar profile to their election victories. Okay. Now, what's interesting is even though they're so similar, they're much closer than any other presidents on the map. They actually get separated when we do our PCA projection, right? So notice that JFK is now more similar to Trump, and Jimmy Carter is more similar to Nixon, even though that's not what we saw when we looked at the 2D space. So this basically hasn't preserved the nearest neighbor relationship. This hasn't preserved the relationships very well. So what ISOMAP is going to do is it's going to draw a nonlinear boundary, a nonlinear projection line or plane or hyperplane, such that we preserve those nearest neighbor relationships. So, for example, I haven't drawn the whole line, but it might look something like this in our case. So notice that with this sort of wiggly line, now Trump is still closest to Nixon and Jimmy Carter is closest to JFK. So we've preserved those nearest neighbor relationships. So this could be useful, for example, if we were doing a recommendation system. So say we're Amazon and we want to do dimensionality reduction on all of our products, and we're only going to give one recommendation. Well, then we could say it's really important that the recommendation you give is that product's nearest neighbor, is the most similar product, the most likely product to be bought. So it doesn't really matter if the distance between that product and some product really far away is still accurate. The really important thing is that those neighbors are kept close together. Okay, let's build on this. Let's think about, actually another one of Trump's favorite activities. There's a little bit of a Trump theme going on here, not intentional. Let's think about crazy golf, right? So on a crazy golf course, if we think about the different holes, the first hole and the last hole in terms of Euclidean distance are very close together, right? They're very, very close. But on a golf course, you don't just go to hole 1 to hole 9. What you do is at every point you jump to the nearest neighbor, right? So you basically traverse the golf course by going always to the nearest neighbor. So if we were to do a PCA projection, again, you can see 1 and 9 are going to be very close together because we can just go straight, yeah. But if we think about it in an ISOMAP way, we're going to create this nonlinear manifold, which is going to mean that that neighbors are preserved. And so that means that now suddenly when we unfold this, 1 and 9 are going to be really far apart. So you can think about it as isomap preserves this idea of what we call geodesic distance, which means that neighbor-to-neighbor distance, traversing the plane using these short hops. Okay, now obviously we're not going to very often be using dimensionality reduction on blueprints of crazy golf courses, so why is this useful in practice? Well, let's start thinking about nonlinear data. So image data is a classic example of data where the linearity assumptions don't really hold. So a lot of you might have come across the MNIST dataset, MNIST dataset, which is basically like a handwriting recognition task. So we have these images of digits, which are 784 dimensionality. So let's think about these three numbers. So we have two 7s and an 8. Okay, now what's really interesting about these is when you think about Euclidean distance, which again is just going to be the distance, the difference or similarity in the pixels, just in the pure pixels, 7 is going to be much closer, the 7 in the middle, sorry, is going to be much closer to the 8 on the right. Yeah, can everyone see that? If we're just looking at the similarities and differences on the pixels. Now this is going to be a problem because if then we do a dimensionality reduction of the MNIST dataset using, say, PCA, it will keep these two very close together, whereas this 7 and this 7 will be much further apart. But let's think about neighbors. If I restrict my traversal of this dataset, my traversal of this plane, to always going by the nearest neighbors, well, to get from that middle 7 to that 8, I'd have to traverse some kind of path like this. And to go from the middle 7 to the end 8, I'd need to traverse a path like this. But the big problem, right, is these aren't really numbers, right? We wouldn't expect anything like this to exist in the MNIST dataset because these aren't numbers. These are just meaningless symbols. So it means that even though the Euclidean distance is closer, right, if we say, no, you need to always traverse by going via your nearest neighbor, then these are going to be quite far apart. There's no way to go straight from the 7 to the 8, except by maybe going the long way round. Yeah. So I'll let that kind of sink in a little bit. It's maybe, I think it can be a little counterintuitive, it can be a little difficult to understand, but this is why we might want to use isomap, which preserves geodesic distance. Okay, and this, you can see this visually. Isomap performs much better on this task. So you can see on the left here we have PCA. So this is kind of quite a mixture of digits. Everything's quite messy. There's no real separation. Isomap, it's not perfect. We'll see in the next section something that will perform perfectly on this, but it does a pretty good job. And again, because it's thinking in terms of that geodesic difference, trying to keep these digits close to their neighbors. Yeah, so it's trying to keep neighbors close to each other, and this then does much, much better when we look at MNIST. Okay, and lastly, just coming back to the Swiss roll. This is what the Swiss roll is all about. So basically, it's saying, no, we shouldn't keep this blue dot and this red dot close together. We should make it go all the long way around by traversing the nearest neighbors. That's why you unroll the Swiss roll, and that's why this is a much better approach for nonlinear data. Okay, so quite a lot to take in there, but the summary is that isomap preserves geodesic distance. The pros is that it works a lot better with nonlinear data, such as images. It's generally quite good for visualizations. The cons are it's much slower than PCA, especially for large data. It might not work quite as well for linear data, where PCA is stronger. And it's not as effective for pre-processing. So PCA is a more general purpose algorithm. And lastly, as we'll see with TSNE does a lot of similar things to isomap, but generally does them better. So we don't tend to use isomap quite so much, but it's still useful to understand. Actually, just one thing on the speed. I didn't show you this, but you can notice that at the top here with the time reading, isomap is way, way slower than principal component analysis. Okay, so our last technique is TSNE. Okay, and this is where it starts to get really complicated to understand. So I'm just going to do a sketch of the internals, but really this is all about the results. You can just treat TSNE as a black box, and it gives amazing, really beautiful results. TSNE stands for T-distributed stochastic neighbor embedding. So a bit of a mouthful, but we can already get some clues of what it's about just from the name. So T-distributed, that implies that it's using probability distributions, which it is. Stochastic implies an element of randomness, not complete randomness, but there's some randomness in here. Neighbor, so it cares about neighbors, just like isomap did. And embedding is just another word for dimensionality reduction, basically. Okay, so here's a very quick explanation of what's going on. So basically, the core of TSNE is it constructs two probability distributions. First, in the higher dimensional space, it creates a probability distribution such that objects which are similar are more likely to be picked together as a pair. And it does the same thing in the lower dimensional space, usually the 2D space, and then it tries to align the two distributions, tries to minimize disparity between them. And one clever thing about it, and again, this is really, to be honest, beyond my understanding, but it uses different probability distributions. So it uses a Gaussian distribution in the higher dimensional space and a student's T distribution, that's where the T comes from, in the lower dimensional space. And basically the fatter tails of the T distribution means that the points are spread out more evenly in the 2D space. Okay, and we have a parameter for TSNE called perplexity, and the low perplexity will mean that we care more about local scale and we focus on preserving local structure. Higher perplexity means that we kind of take more of a big picture approach and try and preserve global structure. But important point here, pretty much all the time, we're going to be focused on preserving local structure. Unless we ramp up perplexity, which we usually don't want to do, we're going to preserve local structure at the expense of global structure. We'll see exactly what that means in a little bit. Okay, so one thing about TSNE is it's randomized. It's partially randomized. So if you run TSNE several times, you'll get different results. So here's an example of TSNE working really successfully. So you can see it's sorting out these various points in a really nice structure. Here's exactly the same data set. And this is just a run that wasn't so successful. So basically what's happening here is that this is getting stuck in a local minima, and it's kind of not getting that same nice distribution that we're looking for. And this is basically because, first of all, TSNE is an iterative algorithm. It uses gradient descent. The gradient descent curve is non-convex, and so that means that we can get stuck in local minima. And so, yeah, inevitably, we might have to run TSNE several times to get the best result, because we can end up with strange situations like this. But the headline is TSNE does like a really fantastic job on all kinds of data. So, for example, if we look at MNIST, this is PCA, you maybe remember isomap. TSNE just does a pretty fantastic job of just sorting out the digits into their own little clusters. And this is pretty amazing when you think this isn't like a classification algorithm. This isn't like some machine learning where we're actually teaching it anything about the digits using training data or anything like that. It's completely unsupervised, but it's still able to create this separation really well. And it's pretty amazing. We'll see in a second. It can even do things like separating different faces of different people. It's very, very, very powerful. The one thing that it doesn't do well is preserve global structure. To be honest, we usually don't care about that. But let me give you an example. Here you can see the clusters for the 2s and the clusters for the 4s are very far apart. And if you've done any playing around with this MNIST data set, you might know that's a bit strange, because 2s and 4s aren't actually that different. They tend to get confused quite a lot. And the idea that our 5s here in the middle are more similar to our 0s than the 2s are to the 4s is very questionable. And to be honest, TSNE's probably just got that wrong. So it doesn't even try and create that kind of global picture generally. So we can't really draw conclusions about, the 2 cluster is on the left and the 4 cluster is on the right. That means they're very different. No, it probably doesn't mean that, to be honest. But what we can say is within a cluster, all of those things should be pretty similar. Okay, so one thing to mention is that we'll usually use TSNE in combination with PCA, right? And there's a couple of reasons for that. First of all, it'll be faster. TSNE can be really, really slow because it's this iterative algorithm, and it will also sort of mediate this problem of destroying global structure. So PCA will care about global structure, and so it will preserve a little bit more of that if we use it together. So this is from the docs for SciPy. It basically says use PCA to get to a reasonable number of dimensions, like 50 dimensions, and then kick in with TSNE. Okay, so the summary is that it preserves local structure. And the pros that it works well for visualization. It can be adjusted using the perplexity parameter. It works really well with loads of different kind of data, complex data, nonlinear data, and it works well with PCA. The cons are that it's computationally expensive, that there's an element of randomness, so the results aren't guaranteed, and it doesn't preserve global structure, generally speaking. Okay, so we've covered all of our techniques now. I just want to touch on a couple of things. First, I just want to show, we've seen this already, but just that side-by-side comparison. And I want to draw your attention to a couple of things. One is the performance obviously improves as we go with these more complex techniques, but also look at the time. So random projection is so fast that in this case, it wasn't even able to really measure a time. Random PCA, again, is like, sub-second runtime, very, very fast. ISOMAP, here we're getting into 1 second, and for TSNE, that's again an order of magnitude slower. And this is a relatively small data set, so obviously these times are going to scale up with the size of and the complexity of the data. And then one thing that I want to touch on very, very quickly, again, this could be its whole own talk, but how do we interpret the reduced dimensions if we want to? So yeah, as we said, we're not going to get these kind of nice semantic dimensions of like performance and cost. So how do we unpick these? Well, there are a couple of things we can do. One thing we could do is we could look at these new dimensions, and we could compute the covariance or the correlation with these dimensions, these new dimensions, and our original dimensions. But what I quite like to do is, if we say have our 2D representation like this, what we can do is we can draw a line in the middle of the axis, the principal component or reduced dimension that we want to interpret, and then basically separate out our data into two classes, those that fall above the midpoint, those that fall below the midpoint, and treat that as class A and class B. And then what you can do is you can just train a decision tree on that data using those two classes. Now, again, if you're not familiar with decision trees, again, probably don't have time to go into them in depth, but basically what this is going to do is it's going to figure out what questions can we ask to separate these two classes of data. So this can be quite an interesting way, and again, it depends a little bit on how many dimensions you have and so on. But for my friend, for example, we could take the data, we could use a decision tree and find, okay, what are the questions that we can ask using our existing dimensions that will most predictively separate these data into the separate classes. And that will give us a fairly good understanding of what that axis is actually telling us. Okay. Okay, so last thing, I want to just talk about some of the cool applications of dimensionality reduction. So there are a ton of different things that you can do with it, so I'm just going to kind of whiz through them. So one thing that is quite nice is you can use them to build recommender systems that have a visual element, which can be quite powerful. And it's pretty straightforward once you've say, taken a bunch of data about the movies that people like. Maybe you're looking at their Netflix data, or what they've rated on social media or something like that. If you take enough of this data, you can aggregate it together. You can say, okay, what movies are similar based on who likes them and dislikes them. And then, if I already really like, Mission Impossible and Terminator, then, maybe the system's able to say, well, you should probably go and check out Expendables 3. So that's one application. So another application is embedding language data. So let's take a simple example and think about emojis. So let's say I have some SMS data. I have a load of these texts, and on each of them I have these different emojis. And I basically build a big matrix of all of these texts and all of the emoji that appear in them. And then what I can do is I can transpose this, so I treat each emoji as its own row, and then I can perform dimensionality reduction on it. And I end up with something like this, which I think is really cool. So the emoji that are similar here tend to be used in similar contexts. The emoji that are far apart tend to be used in different contexts. And again, considering there's no understanding, it's really interesting that you can already see some kind of cool patterns going on here. So there's almost this thing going on here of going from, I don't know, more organic stuff through to your people and your animals up to, your robots and your machines. So, we can already start to make some kind of sense of these dimensions just based on a very naive dimensionality reduction. So this again was done using TSNE. And what's cool about this is we can even start looking at those individual placements of emojis. And because they're vectors in 2 dimensions, we can actually do things like emoji analogy. Okay, so this is basically saying, well, the position of the umbrella relative to the rain cloud is the same as the position of the sunglasses relative to the sun. And because they're vectors, we can just do maths on them. So we can say, well, that means that sunglasses minus sun plus rain equals umbrella. And to me, like, that's really cool. Again, there's no language understanding going on here. This is just dimensionality reduction. Now, if you're, if you've worked a little bit with, kind of vector data, you might realize that actually we can still do this kind of addition and so on in a high dimensional space with high dimensional vectors, but it's just not going to work as well because we have this sparsity problem. So we have this idea of word vectors, which you might have come across before. So Facebook's fast text is a good example of this, where basically they took all the words in the English language, so like 100,000 words or something, and they took all the Wikipedia articles. And so what they ended up with was like 100,000 by 5 million matrix with every article and what words appeared in it. Now, the problem is if you try and do addition and subtraction in that high dimensional space, well, if you've got 100,000 words and 5 million dimensions, there's a real sparsity. There's these huge dimensions, but actually there's only a few words. So if we try and do any kind of addition or subtraction, we're just not going to be very close to anything. But if we reduce these dimensions, so with Facebook's fast text, they reduced it to 300 dimensions, you get something that you can manipulate much better and that produces these amazing results. So you can say king minus man plus woman equals queen. And again, there's no language understanding here. This is just based on dimensionality reduction and based on vector addition. And you can see a bunch of examples here where you've basically got the basis of a question answering system. Again, no NLP going on here in a traditional sense. You've just got dimensionality reduction and vector addition, and this is giving you these kind of amazing answers. So here's a little experiment that I did a little while ago. So you might remember there was this site called We the People, which was basically, we have a similar thing, which is petitions.gov.uk, where basically people could put petitions and then they'd sign on it and petition the government to make changes. This was in the US, though. And they made all of the data open. So basically, I was able to get, and I used Python and Spark to do this, get all of the petitions and basically all of the states that the people signing the petitions were from, and then adjusted that by the population of each state, and then was able to work out, okay, what different issues do different states care about? And then once you've got that data, you can kind of do dimensionality reduction and say, okay, which states are similar, which are different. This was really interesting. Okay, so this comes in 2 parts. So these are 47 states. Okay, so you can see New York is at one end and Wyoming is at the other end, and you've got, the red and the blue shows are they Republican state or Democrat state, so you can see the kind of separation. We're kind of going like left to right here. You've got, Arkansas is way out compared to, like a New York. Pretty kind of what you'd expect. What really surprised me is this is the zoomed in version. This is what we get when we zoom out, right? Okay, so this is 47 states, this is Idaho, this is North Dakota, and this is Utah. So those 2 states, for whatever reason, I still don't really know why, I haven't had a chance to look into the data, they are completely different from all of the other 48 states, which is a really interesting finding, I think. And you can also, by the way, do things like clustering once you've done dimensionality reduction. So again, this is taking that reduced dimensionality and you then do clustering on that, and you can kind of see what would a map of the US look like if we clustered together states that believe in the same things. And clustering in this lower dimensional space works way better because of the sparsity problem that we touched on. Okay, so this was something that I really wanted to do in time for this talk, but I ran out of time to do it. So I'm kind of setting this as a challenge to you. But it turns out that The Simpsons has a really nice data set over at Kaggle, where you have basically loads of information about the script, about different episodes, what characters appear in what different episodes. So you could take that and then you could look at what episodes do characters appear in, what scenes do they appear in, what words do they use, what other characters do they reference. You could build a really nice nice data set like that, then you perform dimensionality reduction to work out, okay, which Simpsons characters are the same and which are different, map everyone out in 2D space. As I said, I was going to do that. I unfortunately didn't have time, so this is not the real outcome. But yeah, could be an interesting way to play around with dimensionality reduction if you are so inspired after this talk. Okay, last couple of applications. So this is from Google. This is really amazing to me. This is called the TSNE map. And it's basically mapping something like a huge number, like 200,000 pieces of artwork in three-dimensional space. And I'll show you a quick video. Basically, what it allows you to do is it's this 3D explorable space of loads of artwork. And it's explorable in 3 dimensions. This is again using TSNE. And it's just, to me, pretty amazing. So I went from Impressionist Hill over to horses. The crazy thing to me is, again, there's no computer vision going on here. There's no, it's not looking at anything apart from the pixel data and using TSNE. And it's amazing just how good a job that it does of sort of separating out all this huge number of pieces of artwork. Obviously, the names here, these are added manually based on the data, but this is pretty amazing to me. And again, more examples of where TSNE performs well. So here we're looking at face data. So again, TSNE is a general purpose visualization algorithm. It's not a face recognition algorithm, but it almost gets most of the way there just on the basis of how good it is. So you can see here pretty much all of these clusters of faces are the same people. And again, this is just TSNE sort of maximizing local structure, trying to keep similar points closely together. And so, yeah, we can do dimensionality reduction on faces, and that's actually maybe the first step in a more sophisticated face recognition algorithm. And this brings me on to my last application, which I love. So again, this is talking about using face data and dimensionality reduction. But this is a different story altogether of somebody called Justin Long. And so he was a software engineer. He was single, but he really wanted to be in a relationship. But he just found things like Tinder he wasn't getting enough matches, or it was very time-consuming. So he thought, okay, can I automate this process? So basically, what he did is he took the faces of people that he would swipe right for versus the people he would swipe left for. Now, obviously, this is very high-dimensional data, so he had a matrix of these very high-dimensional face images, and you can't really do a lot when you have such high dimensionality, right? It's very difficult to say, okay, is this similar to someone I would match with? But if you do dimensionality reduction, you can reduce that data down, and then you can kind of zero in on what are the key differentiators. So on the left, I think on the left is the people he would swipe. I don't use Tinder. He would swipe no for. On the right are the people he would swipe yes for. And so then he was able to use that, and then he built a program to basically automate his Tinder, and then he also combined that, I think, with a chatbot to do the initial back and forth. And so what you're wondering is probably, did it work? And so I'm happy to say that this is a recent blog post. So the burning question is, did I solve my own problem? The answer is a resounding yes. In the interest of privacy of my relationship, I won't be publishing too many details on the blog, but I will leave you with a picture of myself with the most beautiful woman in the world. So dimensionality reduction can not only help you get more meaning on your data, be a better data scientist, who knows, it could even help you find love.